Vsauce, Joshua here. Today we will be learning about the Slinky Paradox and essentially how this seemingly physics-defying motion is rather a very interesting phenomenon about how forces propagate through certain materials. And so we'll be seeing what are the misconceptions with this and how do we develop an intuition by deriving the governing equations around it, and then maybe looking at a simple mathematical model, and then how does our mathematical model relate to physical data.
So let's get started. So we're going to have an introduction, define the continuous model, Newton's law, Hooke's law, and the wave equation, and then how we do a discrete mass spring model for computational methods. So the Slinky paradox is essentially what I was saying earlier. It's that you have a slinky, you hold it up into a static state, you let go of it, and the bottom seems to hover while the top seems to fall down until it collapses and it falls down. That is essentially the essence of the Slinky paradox. And this feels wrong at first because we're like, oh, when I drop something like this ball, it falls. And so logically, if I let go of the top, that bottom should fall. But we're going to see why exactly it doesn't fall. And it's just due to a very unique relation that we don't intuitively think. And so in reality, we're going to see that the reason it changes or it doesn't move is due to the fact that springs act like waves and they have a finite wave speed. And because a spring has a very slow wave speed, we can actually observe it with our own human eyes. And so another thing to note is that tension higher up on the spring will be higher than it will be lower, but that doesn't play too much part in our scenario. So how do we kind of develop an intuitive sense? We're going to look at how to set up a clear model of a slinky, and we're going to say, okay, we can break it into a small part, small masses that each can have a strain, and then we're going to use Newton's second law on those small parts, and then we're going to use Hooke's law to find a relationship between the tension and our spring constants, and then we're going to get an equation that looks like a wave equation. And so here at the bottom you can kind of see a data analysis I did of like, okay, you see at the top that blue line is the highest point of the slinky. As it drops, it starts collecting the points below it until at the end over here, it's completely collected all of it. And that's kind of what you would observe watching a slinky fall. And so kind of getting how do we develop that intuitive sense, we're going to define a continuous model, basically a smooth spring. It's just an idealized kind of cylinder spring. And we're going to define epsilon as the measure position along the slinky. So basically it's a way to divvy up by stating that the top of the slinky is 0 and the bottom is 1. And we're going to let the vertical position of that point that we started at epsilon be y. And we're going to define that for the entire idealized smooth spring that we have a mass per unit length called rho, basically our linear density. And then we're going to define a tension, which is basically the tension between each we're going to divvy it up and basically say how much does the slinky at top pull or the slinky parts below it pull. And so we're going to look at this small part, as you can see here, of from epsilon to epsilon plus delta epsilon. And it's going to have a mass of rho times delta epsilon, and it's going to have two tensions. The tensions from below, which is because we're going to be looking at a downward positive in this scenario, it's going to be defined as this, which is just the tension from the point past delta epsilon, and the tension from above is just going to be the points before delta epsilon. And then we're going to have the downward weight, which just is mass times gravity. And so that when we put this all into Newton's second law, where we have the downward force minus the upward force plus the weight is equal to the mass times acceleration. And so then we can divide out delta epsilon, and using our tools from calculus, delta epsilon will only be left on the two tension forces, and we can use one of the fundamental theorems of calculus to basically say, oh, this is going to be a partial of the tension with respect to epsilon. And so then we're left with this balancing equation. And so now that we want to have a tension here, we want to get it into something we can manipulate easier. So we're going to connect tension to stretch using Hooke's law. And we know that for a uniform spring, the tension is equal to the spring constant times the strain. And so knowing this and knowing that we have a uniform spring, we're able to use this. So we take back that balancing equation and we're basically like, hey, let's plug that in. So we plug in our tension relation and we get this balancing equation. We divide out rho and we get a very unique equation where we have an acceleration. An acceleration is equal to the is equal to, oh my goodness, the words are blank, a constant plus a stretch. And so it's okay. Now we know what we're getting with here. And so we basically can take these two constants and find them as a new constant c, and then our equation becomes this, where c is defined as a wave speed along the slinky, because this is just a wave equation plus gravity. And so we want to kind of get rid of that gravity term because, we were able to get rid of it, but we can remove it so we can get a more easy to understand equation by just letting a new function called the y equation, which is basically the position of each point when the slinky is in that static state. And then we define this new equation, which is u is just equal to the current position minus the equilibrium position. We plug that back into our previous balancing equation. Gravity will cancel out, and we are left with a one-dimensional wave equation. And because we were able to derive a one-dimensional wave equation, this tells us that a slinky, when there is a force amongst it, it propagates like a wave. And so what we are basically able to have is that the acceleration of any point epsilon here on this left is equal to it's the speed of its change of its neighbors, so how its neighbors are changing, times a finite speed. So this is how fast essentially it can change. So it only really changes based on its neighbors, based on this finite wave speed. And we know that from how waves behave. And so what we're able to say is like, okay, a slinky has the behaviors of a wave. That explains like when you release it, the information of the way release is not propagating until it hits whatever point epsilon you're looking at. So the change in tension and position move as waves with speed. And so when the top is released, only coils near the top feel it right away, and then it has to travel down, 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 down. And so until this wave reaches a coil, that coil will basically still be held up by the old tension. And this is what the Slinky Paradox is. It's the fact that slinkies, when you release or change it, the force has to propagate like a wave, and it takes time because the wave speed is very slow. And so computationally, we can state that we have a simple chain of n plus 1 point masses, each with a mass m, and they're connected by n identical springs, each with a spring constant k and a rest length of L. And so what we basically say is that let y of I be the vertical position of any I mass that we have, with I being 0 being the highest one and I being n being the lowest one. And so that for any spring in between, we have that the spring, basically the spring equation, or the Hooke's law for it, basically the stretch of it from the top one times spring constant, and the stretch from it to the bottom one times the spring constant plus the force due to gravity, is how that whatever I mass you're looking at will behave. And we can see this in our model. As we can see on the right, we have the real world data, and it's very similar to our computational data on the left. And we kind of see, oh, we got the same results using computational method. Of course, the computational method graph is a lot more prettier because you're not having to click it by hand. But it's the fact that we have this relationship that, okay, it's going to move. And we still see the same behavior that the closer the top mass gets is, it kind of pushes down because it's compressing the springs between the highest mass and the mass below it, and it's pushing it until it collides, and then you get this cascading behavior. And we kind of see that on the right in the real world data too. And so overall, we've kind of now should have an intuition for how the Slinky Paradox works, because the force changes in tension move the Slinky at a finite speed c, not instantly. And that finite wave speed is slow enough to where we as humans can perceive it. And so we were able to use Newton's second law on a small piece of an idealized spring, and then use Hooke's law for the spring and then we were able to get the wave equation for motion along the slinky. And so we were basically able to show that the top will start to move, and then it'll transmit the force as a wave, and it propagates down until the bottom will hang until the wave propagates there. and hits the bottom. But for Slinkies, the reason it seems like it's not until the top crashes is because the finite wave speed is very close to the speed of which the Slinky will drop. And so this explains the paradox and connects the video I've shown, the math, and a computer model. Thank you.